Okay, so we continue this course of classical field theory. We begin today a new chapter, which is the relativistic dynamics. You know, dynamics is about studying the motion, the equations of motion as in classical mechanics, but in a relativistic form using Lagrangian action principle, least action principle, etc. So we will consider a free particle, which means there are no external forces applied to this particle. So as in classical mechanics, we consider a free particle moving in space-time between point A and point B. So starting at A, going to B according to a certain trajectory between A and B. So it's a world line, it's a trajectory, a world line in space-time between point A and point B. This trajectory we can divide it into several intervals, small intervals, and for each interval we can define a position vector or a position 4 vector and a 4 velocity corresponding to this small interval, differential interval between A and B. So it's a free particle moving from A to B according to a certain trajectory. So we need to find the laws of motion as in a classical way, as in a Newtonian way. We need to find the equations of motion analytically. So we need to work equations. So we have a very important quantity, physical quantity to determine, which is the Lagrangian. The Lagrangian is a quantity that is supposed to be in any equation of motion in order to determine the action or the displacement or the motion between point A and point B, which takes us to the principle of least action. You have to remember in classical Newtonian physics, the things you learned last year in classical mechanics and analytical mechanics about Lagrangian and the principle of least actions, which governs the motion between 2 points in space or in space-time in our case. So these laws of motion have to be the same in all inertial frames, which means they have to be invariant. You know, in physics, we only work with invariant quantities and always invariant quantities. Non-invariant quantities are not laws of physics. So always pay attention to this condition. All laws in physics have to be invariant in inertial frames. Otherwise, they would not be called physical laws. So when a free particle goes from A to B, it goes along a trajectory. We get a trajectory that minimizes or maximizes a quantity that we call the action. Maybe last year or maybe in other courses you are used to call it J, the Jacobian, or the action of Jacobi, or whatever you call it before, or you are used to call it before. This quantity we will call it the action. All reference books and all references now they call it the action. So this quantity is the action. So by moving from A to B, we have an action that determines this trajectory according to a certain quantity, which is the Lagrangian. This action also has to be in frame independent, so it has to be invariant. And if we are dividing our trajectory into small trajectories, into small differential trajectories, so the total action would be the sum of a series of very small actions along the trajectory, each one along or each one taken on one interval in on the trajectory. And the integral itself, which is the action, should be also frame independent. So it should be invariant by Lorentz transformation and all inertial frames. So here you have to be you have to pay some attention to these conditions. So I will go a little bit slowly because analytical mechanics is a little bit difficult. So I need your attention here, especially on this and the next 2 or 3 videos. Okay, so it's a motion between point A and B. A and B are fixed. We have a trajectory. Why do we have a trajectory for a free particle with no forces applied, with no external forces applied? Why do we have this trajectory? Because this trajectory is conform to the principle of least action. This is the trajectory that minimizes or maximizes the action for a free particle. Okay, we know about invariance between 2 points, and the most important and the most famous invariant quantity is the proper time, which is the only quantity that we can use in such calculations and in this type of equations. So the proper time with delta tau, which is the same in all inertial frames, which means that all observers, all inertial observers, will agree on the same quantity delta tau, which is the proper time. So if we have several intervals on the trajectory, so the actions, the total action would be the sum of all these small actions. They have to be function of delta tau, because delta tau is the only invariant to be used in this calculation. So the starting and finish points A and B are fixed. So by analogy to classical mechanics, we have to consider the trajectory that makes the action extremal. Extremal, which means a minimum or a maximum. This is the real trajectory of a free particle between A and B, is the trajectory that makes the action extremal. Extremal, which means a minimum or a maximum. You can use the plus, you can use the minus, whatever. It could be a maximum and it could be a minimum. So the trajectory, the real trajectory, is the trajectory that follows the least action principle, which is a stationary action. So it would become a stationary action. As in classical mechanics, you have 2 fixed points. The trajectory between these 2 fixed points is it's the trajectory that follows the principle of least action, and that minimizes or maximizes the action. In this case, for example, you can imagine the string of a guitar. The endpoints are fixed, and you have a wave that can develop between these 2 fixed points at a certain frequency. Of course, this is not the same, but it's close enough to imagine how a stationary motion or a stationary trajectory is obtained between two fixed points in space-time A and B. Okay, the action is invariant, so you can multiply it by a scalar, positive or negative or whatever the scalar is, or you can add or subtract, you can add or remove scalars, and it doesn't change anything of the equation. It doesn't change the physics of the equation. So if you have an invariant quantity, you add a scalar, or you remove a scalar, or even if you multiply by a scalar, it doesn't change the physics of the equation. The physics is the same, whether you multiply it or you add a scalar to the equation. This would be useful when we see the mass in our Lagrangian. So it's analogous to, it's the analog of a classical system where the shortest distance between 2 points is invariant. Here, in space-time, the shortest distance between 2 points in space-time is simply the proper time. And you already know about this. So our total action is the sum of all many actions on each interval. So it's, if you have n interval, we multiply by n. So it's n times the sum of delta tau with a minus sign. The minus sign here doesn't have any physical meaning. It's just a convention that was adapted by classical physicists even before Einstein, before relativity. It's just a convention. So we will use this convention to find classical equations when we are moving at very slow velocities or very small velocities. So it's just to find the classical equations when you are at small velocities. So the minus sign here is not a physical quantity. It doesn't have any meaning in physics, just a convention. You can use the minus, you can use the plus, but everybody uses the minus sign. All reference books use this minus sign, so we will use it. It's a convention not related to physics, but or maybe related more to mathematics, just to be able to find the classical equations. Okay, so you know when you have a sum over very small quantities, or over differential quantities, the sum becomes an integral. So this action, the total action, is the limit when delta tau tends to 0 of this quantity minus n sigma delta tau. So it becomes minus n integral of d tau as a differential quantity. And you know that d tau is equal to the radical of dt squared minus dx squared. So the equation is minus n integral of radical dt squared minus dx squared. And if you put the dt outside of the radical, so you will get minus n integral of radical 1 minus v squared, the same famous radical of 1 minus v squared dt. So you know, in classical mechanics, we have this way in notations to consider that the v, which is the first derivative of the position vector, which is in this case dx over dt or over d tau, we have this convention to write the first derivative as an x dot, or the quantity dot. The double derivative is x double dot, etc. So instead of v, we will use x dot, which is the derivative of x with respect to time, which is the velocity. The velocity is the derivative of the position with respect to time. So it's the derivative of x, so it's x dot. So instead of v squared, we will use x dot squared. So our action is minus n integral the radical of 1 minus x dot squared dt. So you see, this is an integral that depends on the speed, on v, which is x dot. Or in the classical case, the integral should be dependent on a quantity that we call the Lagrangian. You know that the action is the integral of L dt. So it's the integral of some quantity that we call the Lagrangian. So we will do the same in relativity. And you know also that the Lagrangian itself depends on both the position and the velocity, x and x dot. But for a free particle, which means in the absence of external forces, it will only depend on the speed, on x dot. So that's why here, when we consider a free particle, our action is only dependent on x dot, because it's a free particle, no external forces apply. But if you consider a motion with external forces applied, you will have or you will get another term as a function of x. But the most easy here and the most direct way is to use, as in classical mechanics, a free particle with no external forces, and to determine the equations of motion for the case of a free particle. So our Lagrangian will only depend on x dot, on the velocity. Okay, so we are using a free particle. The integral depends on the speed. So L, which is the term inside the integral, the minus n, you put it inside because it's a scalar. You can put it inside of the integral or outside, whatever. It's a scalar, doesn't change anything. So the quantity minus n times the radical of 1 minus x dot squared is the Lagrangian, because it is the quantity inside the integral that determines the action. Okay, you can use the entire space x dot squared plus y dot squared plus z dot squared, if you have motions along y and z. Or you can simply use the x dot squared if you have motion only along x. So our Lagrangian is minus n radical of 1 minus v squared, which is the relativistic Lagrangian. Our relativistic Lagrangian, so it's minus n radical 1 minus v squared. Or if you remember, the classical Lagrangian is half mx dot squared or half mv squared for a free particle. So the Lagrangian, the Newtonian Lagrangian of a free particle is like the kinetic energy, half mv squared or half mx squared. But in relativity, so the Lagrangian, the relativistic Lagrangian of a free particle is minus n, and now we will see about n later, radical 1 minus v squared. So wherever you go, whatever you do with your equations, you will always find this radical of 1 minus v squared, or radical 1 minus v squared over c squared if you are taking c different from 1. So the importance of this Lagrangian is that it puts the motion, of course, of a free particle in a form that is frame independent. So it's independent of any inertial frame, or it's the same in all inertial frames. So it's an invariant quantity. We can use it in physics. It's an invariant quantity. So the action, because it is built from invariant quantities, it will be the same in all inertial frames, which also makes the action stationary, as in the Newtonian case. And now, as we always do with our relativistic equations, we consider the case for low speeds or for small velocities. Of course, the radical of 1 minus v squared, when v squared is very small, or v squared over c squared tends to 0, this is 1 minus v squared to the power half, 1 over 2. So it's 1 minus half v squared, etc. So L is minus n times 1 minus v squared over 2, etc. So it's minus n minus times minus plus n v squared over 2. You see, this Lagrangian at low speeds should be the same as the Newtonian Lagrangian, as half mv squared. So the quantity n v squared over 2 is the same as the classical Lagrangian of half mv squared. So the number n is nothing more than the mass m. The scalar n, when we multiply by the scalar n, this scalar n, we find that the scalar n is nothing else than the mass m. So here you can see the meaning of the mass m, which is the same for all speeds, for all rays. We will see about that in the next slide or two. So at low speeds, when the Lagrangian converge to the classical Lagrangian, to half mv squared, so L is, we replace m by m, it's minus m plus half mv squared. So this half mv squared, which is the Newtonian Lagrangian. And as we already said before, it's an invariant quantity. You can add a scalar, you can remove a scalar. It doesn't change the physics of the equation. So if you can remove this minus m, or you can keep it, it's the same. Your Lagrangian is the same as the classical Lagrangian half mv squared, which is equal to the kinetic energy of the object. So our L is minus m plus half mv squared in classical, or as we will see, we will consider the quantity m and the relativistic Lagrange. So the quantity n is the mass. So here in the relativistic Lagrangian, so our L is minus m radical 1 minus v squared. So our scalar n is nothing more or nothing else than the mass m. Okay. Let's go to the momentum and the energy. You know that the total momentum and the total energy are conserved, especially for isolated systems. You can even use the entire universe as an isolated system. The total momentum of the universe and the total energy of the universe or any isolated system are conserved. So these two quantities are conserved. So let us calculate the momentum along x, p of x. By definition, you know, in Newtonian, you have this way to write that p is equal to m times v in the classical mechanics. But p equals mv is not the definition of a momentum. Here I am talking about the linear momentum, of course. So the momentum, by definition, is not m times v. When you calculate it, you get m times v. But the definition of the momentum is the partial derivative of L, the Lagrangian, with respect to v, or with respect to x dot. So by definition, px is del L over del x dot, not just mv. In classical mechanics, when you calculate the partial derivative, you get m times v. But by definition, is del L over del X dot. So it's del of the Lagrangian minus M radical of 1 minus X dot squared, Y dot squared, plus Z dot squared over del X dot. So the variable is X dot. So we consider the derivative of radical 1 minus X dot squared. So it's minus 2X dot over 2 because you have a radical. So it's minus M times minus 2X dot over 2 radical of 1 minus V squared. Minus and minus, you get a plus. You can remove the 2 on from the equation, so you get mx dot over radical of 1 minus v squared, or x dot is the velocity along x, so it's vx. So mx dot over radical 1 minus v squared is mvx over radical of 1 minus v squared. And you already know from the 4 velocity, the 4 vector velocity, that Vx over radical of 1 minus V squared is the x coordinate of the 4 velocity. It's ux. So P of x in relativity is equal to m times ux. So instead of having m times Vx in a Newtonian case, we have m times u of x in a relativistic case. So it's just like if we have replaced the 3D velocity by a 4D velocity. A 3D vector, we replace the 3D velocity by the 4 velocity. So we are using a 4 vector instead of a 3 vector. So P of x is m times u of x, which is the relativistic momentum, linear momentum, of course, along x. It's the same for y and z. P of y is m times u of y, and P of z is m times u of z, etc. Here, let's talk a little bit about the mass m. M is always the mass, the quantity taken at rest, which is the inertia of an object. And I will repeat it, and you have to stick it in your brain and never forget this in physics, if you are a physicist. M is a quantity that is measured at rest. There is no such thing as a mass at rest or rest mass or a mass in motion or motion mass or whatever you are used to say in previous courses about relativity. There is no such thing as a rest mass or a mass in motion. The rest mass, the term rest mass is not used anymore. Now we do not talk about a rest mass or any kind of mass. There is only one kind of mass, which is the mass that is measured at rest, because it's an intrinsic property of the particle. It is its inertia, which is independent of the motion. The mass is independent of the motion. The mass is mass, nothing else. Not mass in motion, not mass at rest. The mass is mass. For example, the mass of an electron is the same, whether it is accelerated in a cyclotron, whether it is moving around the nucleus of an atom. The mass of the electron is always the same. What comes as an addition is an energy, not a mass. So when an object is at rest, the mass is always the mass, but it is equivalent to the energy at rest. So we have an energy at rest and an energy in motion, but not a mass at rest and a mass in motion. So the mass is mass. The mass is the same, whatever is the velocity. What we will add to the mass is energy, not mass. So we have a rest energy and we have an energy of motion. Okay, so the mass is the same, it's the mass, simply the mass. So let's go back to the linear momentum, P. It has three coordinates, px, py, pz, as a three vector. These quantities or these coordinates are proportional to the four velocity. M times ux times uy times m times uv, etc. But the total momentum is conserved. So if you have a group of particles, the initial P, the initial momentum, should be equal to the final momentum. So P initial minus P final should be equal to 0. But you know, in physics, we need invariant quantities. And in space-time, we need 4 vectors, not 3D vectors. So we will verify this invariance of the conservation of momentum by working out the zeros coordinate or the time coordinate. So we will consider the momentum as a 4 vector to verify the invariance. We will consider it as a 4 vector. So here we have to add the P0, the force coordinate or the time coordinate or the zeros coordinate, whatever you call it. We have to add this coordinate in order to get a 4 vector, which would be the 4 momentum. So P0 should be equal to m times u0, because Px is equal to mx, Py is equal to muy, Px equal to mux, etc. So P0 should be equal to mu0. So let us see about that. Let's find the energy. And you know also from analytical mechanics that the energy is related to a quantity called the Hamiltonian. So you have to remember the Hamiltonian from last year, from the course of analytical mechanics. So the Hamiltonian H is the sum of x dot of I times P of I minus the Lagrangian L. This is by the definition, which is the same definition of the classical Hamiltonian. Definitions are the same always, in classical or in relativity or anywhere. Definitions are always the same. So the P of I, so it's m times u of I, so it's mx dot of I by definition over the radical of 1 minus v squared. And L is the relativistic Lagrangian, which is minus m radical 1 minus v squared. We replace in the Hamiltonian H. So it's the sum of x dot times P of I, so it's mx dot I over the radical of 1 minus v squared, minus L, so minus minus, so it's plus m radical of 1 minus v squared. X dot I times x dot I is x dot I squared, so it's v squared. X dot is the velocity. So it's mv squared over the radical of 1 minus v squared plus m radical 1 minus v squared. So you do the same denominator as you do it always. So you get mv squared plus m times 1 minus v squared. So radical times the radical, it's 1 minus v squared. So it's mv squared minus mv squared. So you get m over radical 1 minus v squared, which corresponds to u0. If you remember the 4 vector velocity, 1 over radical of 1 minus v squared is u0. So m over the radical is mu0, which corresponds to p0, which is the Hamiltonian. So it's the energy. So this quantity mu0 is at the same time is equivalent to p0, the zeroth coordinate of the momentum, and it's at the same time, it's the Hamiltonian, and it's the energy. So mu0 is the energy, so it is invalid. Okay. For low speeds, radical 1 minus v squared, so it's 1 minus v squared to the power, if you get it on the upper side of the equation, so it's 1 minus v squared to the power minus half, and if v squared tends to 0, it's 1 minus, so it's 1 plus half v squared. So so it is equal to m plus half mv squared. Or if you arrange the dimensions, if you add the over c squared, so m over the radical 1 minus v squared over c squared is mc squared plus half mv squared, which is equal to the energy. So the energy of any particle, or the Hamiltonian of any particle, is mc squared plus half mv squared. So if your object is at rest and v equals 0, the energy is reduced to mc squared. So E is equal mc squared, which is related to m, the inertial mass. Okay, so this mc squared, E equals mc squared, is the energy at rest. M is the mass, which is the same everywhere. But mc squared is the energy at rest. So when an object is at rest, it has an energy that is equal to mc squared, which is his rest energy. If the object is moving with a speed v, you add its kinetic energy. So it's mc squared plus half mv squared. Okay, so the total energy is the sum of a rest energy and a motion of, or the energy of motion. It's mc squared plus half mv squared. Of course, when we say at rest, we mean that the center of mass of the object is at rest in its own frame, is fixed in a frame. But of course, the molecules of the object are never at rest. If you go on a microscopic level, you know that molecules are never at rest, unless you are at a temperature of absolute 0. If you are at 0 K, okay, maybe your molecules will be at rest. But if you have, if you are at any temperature different from 0 K, your molecules are never at rest. But if you take the macroscopic object, its center of mass, if it is fixed, so you say that the object is at rest. But molecules are never at rest. So this quantity c squared is the term that allows you to make the conversion between the two forms of energy, or between mass and energy, from mass to energy, or from energy to mass. You multiply the mass by c squared. Let's take some examples. The energy is m over radical 1 minus v squared. Okay, So if your object is moving with a speed c, so your v squared tends to 1. Okay, so the radical is a radical of 1 minus 1. So the denominator will tend to 0. So the energy is m over 0, which would be infinite. Okay, physically, this means that you have to put an infinite energy to massive objects in order to move them with the speed c. So if you need to displace or to move your massive object with the speed c, you need to put infinite energy on this object to obtain the velocity c or the speed c. That's why it is impossible unless you can get infinite energy. And the same applies for momentum. mv over radical of 1 minus v squared, if v squared tends to 0, so the quantity will tend to infinity. So it means if you are using a force or an impulse, momentum, linear momentum is related to the impulse. So if you are using a force to push an object or to accelerate an object to the speed c, you will need an infinite force in order to accelerate it to the speed c. So it is impossible to move massive objects. Any object that has a mass different from 0 will not be able to move at the speed c, because you will never get infinite energy, you will never get infinite forces, at least in this known universe. For massless particles, for photons, for example, the speed is always c. The speed is always c and the mass is 0. So m is 0 and the denominator is 0. So the energy is equal to 0 over 0. 0 over 0 is mathematically indeterminate. Okay, in mass, they tell you that it is indeterminate. But in physics, indeterminate means that this energy could take any value. So any value of the energy for massless particles would be a valid value, would be a true value, which applies to all photons. Photons have all the same speed, which is c, but not the same energy. You know that photons, if you take the visible spectrum from red to violet, for example, the red photon and a violet photon, they both have the same speed in vacuum, which is c. But the energy of the red photon is less than the energy of the violet photon. Okay, so the violet photon has more energy, has less wavelengths, has more frequency. You know that. They have different energies, but the same speed, which applies to any electromagnetic radiation, to microwaves, to infrared, to ultraviolet, to gamma rays, to visible rays, to any kind of electromagnetic photons. So they all have the same energy, the same speed, c, but not necessarily the same energy, because their energy is mathematically indeterminate. So it can take any value and it would be true. So the difference between photons is not by their speed, because they all have the same speed. The difference between photons is through energy that has to be expressed in terms, or could be expressed in terms of momentum. And classically, on a Newtonian case, we have E equals half mv squared, which is the same as saying p squared over 2m. Okay, this is a Newtonian case, but In relativity, in reality, if you remember the norm of the 4 speed or the 4 velocity, u squared is equal to 1. So we said before that it is a positive quantity, so it's a time for vectors, etc. So the norm u0 squared minus ui squared is equal to 1. If we take this equation and we multiply it by m squared, it's an invariant equation. You can multiply it by any scalar, m or half m or m squared or any kind of scalars. The physics would stay the same. So if we multiply by m squared u0 squared minus m squared u squared is equal to m squared, of course. mu0 is the energy, so m squared u0 squared is E squared. M times U is the 3 momentum, the 3 linear momentum, mux, muy, muz. So it's m squared u squared is momentum squared, 3D momentum, the 3 momentum. Here as a notation, you can write it as P with index 3D, or you can put a lowercase p, a minor p, lowercase p squared, which means is the 3 momentum, which is equal to m squared. So the energy E is equal to the radical of p squared plus m squared, p3 squared plus m squared. Or if you arrange the dimensions, you will get the famous equations that you already know from previous courses. E is equal to the radical of p squared c squared plus m0 squared c4. Okay? So for a photon, the mass is 0. So the energy will be reduced to the radical of p squared c squared, or c times the absolute value of p. Of course, we don't get the negative, or we don't consider the negative value of p, because we don't have negative energies. Or theoretically speaking, maybe we have negative energy. But in this case, in a practical case, we consider only the absolute value, the positive sign of P. So E is equal to C times P, which is true for photons, for gravitons, for almost true for neutrinos, because neutrinos have mass, but a very, very small mass. So you can apply this to neutrinos. Okay, I think I will stop for now. I think it's enough for this session. We will continue with further videos on the next session.